Etienne?
Yes, I am here.
That's
Can you hear
already
me?
a good starting point. Maybe second starting point is maybe it's time to maybe we wait a minute, then you could start to upload. Or maybe I just keep this, we keep this and then you can upload your slides, isn't it?
Oh, I can start now. I mean, to share my screen.
Yeah, do this. Yeah, it's here.
Okay, great.
Seems to be that the cursor works too. Maybe you can forward. Can you forward?
Sorry?
Can you forward one slide? Yeah, that works too.
And you see my cursor too.
Yeah, cursor is fine.
Perfect.
Okay. Good. So we got another 3 minutes. Thanks, Mackenzie, for managing the chat.
No problem. My pleasure.
No, very well done. Thanks.
Yeah, it's great. It's exciting so far. So this is really nice. So.
Yeah. Thank you.
Of course.
Okay, Mackenzie, if you want, then you maybe can manage this session. Then, okay, good. I hope you're all back. Let's start with our second round. Quickly for the newcomers, if you have questions or you want to ask a question, you can go to the Q&A section that you just go down at the button of your Zoom. And you can post a question, and there's a small committee that decides which questions to ask. And it's also on you to upvote or downvote a certain type of question. We usually ask the question which got the most votes. There were a couple of questions. Yes, we are recording the talks, and we will publish them most likely on YouTube. Okay, without further ado, I'm happy that we have Etienne Koechlin as our next speaker. And Etienne, the floor is yours.
Okay, thank you. Good afternoon, everybody. I would like to first thank the organizer of this workshop for their invitation. I'm sorry I cannot go back to my first slide, so I'm starting with my second slide. So I'm going to talk today about computational imprecision as a source of human adaptive behavior in a changing environment. So the general idea is that the brain is a physical device, and of course precision of neuronal computation is therefore limited. And what we observe in previous studies, that computational imprecision rather than algorithmic deviation from optimal adaptive process dominantly contribute to choice suboptimality in stable environment. And we show that using some bias variance decomposition procedures, that suboptimal choice comes from 2/3 of suboptimal choice come from this kind of computational imprecision rather than some algorithmic distortion, something like temporal bias or spatial bias or unknown distortion. So the question is, so of course computational imprecision may explain cognitive bias as optimizing information processing in imprecise brain processes. For example, recency effects is a useful heuristic in when computations are noisy, because you rely more on more recent information, and which are less noisy because it's less computed. However, we observe that these imprecisions are actually very important, and the question is why evolution has favored so poor computational precision in inferential processes. Because it's easy actually to decrease this imprecision just by adding a lot of number of neurons and so on. So our hypothesis is that in uncertain and changing environment, computational noise that follows the Weber law dismisses the need to infer the volatility of external contingency, that is the rate of change, for optimally guiding sequential decision. And if it's the case, if it's true, it's a great evolutionary advantage, because we know that inferring the volatility of the environment is rapidly become computationally intractable in a natural environment. So what is the Weber law? The Weber law means that imprecision in internal representation scales with the magnitude of change in internal representation. That is, you have some belief, for example, and you update this belief, then your updating is noisy, with a noise which depends on the size of the update. So here you have some previously proposed model of inferring volatility. So here you have the classical models from Timothy Behrens, where you have stimulus, action, you get a reward, and from this observable you infer some hidden state, but you assume that there is a volatility, that is, that the hidden states can change with a given probability from time t to time t plus 1. And you assume in addition that your volatility by itself can vary across time. So this is a quite complex model which becomes rapidly computationally intractable. You have a more simple model where you assume simply that this is very similar, but you assume that the volatility is constant across time. And then you have, of course, a very simple model which is not very adaptive. That you assume that hidden states are actually stable over time. That is, there is no change. You assume no change in the environment in the external contingencies. And what we know, of course, is that this model is a theoretical adaptive optimum in environment with variable volatility. This one is optimal in environment with constant volatility, and this one is optimal in stable environment. So as I said before, this kind of model are computationally intractable, but some recent sequential Monte Carlo particle filtering methods are able to compute the exact inference. But this method uses both forward and backward passes to emulate exactly this inferential process when the number of particles increase to infinity. But of course, this is biologically implausible. There are some approximation of this SMC2 procedure which only use forward passes. And there are even some neuronal implementations that have been proposed to approximate this kind of particle filtering method. And of course, this model is very simple and it's computable in closed form, but you can also implement it through particle filtering neural implementation. So the Weber imprecision model is basically a zero volatility model. So it assumes that the environment is stable, but you add some Weber noise in the updating process. So we use forward sequential Monte Carlo procedure to implement this model with additional noise in the particle filtering. That is, each particle may misjump from one to another latent state between trial t and trial t plus 1 with a given probability epsilon, where epsilon is a uniform distribution with a variance that vary as the quantity of update. So this is the Weber law. And of course, you have two free parameters, the constant noise and the Weber component. That scale the Weber component. So we first perform some computer simulation. So we have a protocol with binary feedbacks. And for each stimulus, one action leads to feedback, to the positive feedback with probability eta, and other action lead to feedback to the negative feedback with probability 1 minus eta. So eta is 10% in the simulation, but of course need to be inferred by the model. So we simulate the model in the stable, constant volatility and variable volatility environment, each included 1,000 successive trials. And we simulate closed environment, that is, we have only one stimulus and two possible actions. So it's basically a two-arm boundary task with reversal. And also we simulate in open-ended environment or quasi-open-ended environment with 3 possible stimuli, 4 possible actions, and which means 24 possible stimulus response mapping. So we have 24 latent states. So here this is the full varying volatility model. So the model infers the volatility, the reward probability, and the rate of change of probability, and also gamma is, especially in the open-ended environment, this is the possible reoccurrence probability of hidden state. So the full constant volatility model, the same without the higher hierarchical level of Bayesian inference about volatility. And then you have the zero volatility model, which infers only eta and the parameter gamma. And then we have our Weber imprecision model, which is the zero volatility model plus this Weber noise. So in stable environment, as I said before, this is the result of the simulation, the model performance. And the zero volatility model is, of course, the optimal model. The Weber imprecision actually is a more general model because it's a zero volatility model plus additional parameters. So, of course, it's performed optimally in this stable environment. And the same for the the reinforcement learning model. So here it's a Pearsall reinforcement learning model with possible noise. And here you have the zero volatility model plus a softmax function. So of course, all these models perform optimally in the closed environment. In the open-ended environment, the noisy PHRL perform lower because, of course, it cannot use information about, it make no inference about the reoccurrence of the possible reoccurrence of hidden states. So more interestingly, in changing environment with a low volatility, now the theoretical adaptive optimal is the exact constant volatility model. Here you have its forward approximation, so which is almost which perform optimally, quasi-optimally. You see that here the Weber imprecision model perform also quasi-optimally, whereas RL models plus noisy selection model performs in unstable environment. So we have similar results. So now the theoretical optimum is the exact varying volatility model. Its forward approximation perform quasi-optimally, and the Weber imprecision model perform also quasi-optimally. Whereas again, the RL models and the noisy selection model perform suboptimally. And finally, in changing environment with a very high volatility, constant but high volatility, again, we have the same results. The Weber imprecision model perform quasi-optimally, whereas both the RL models and the noisy selection model perform suboptimally. So the first result is therefore that in every environment, the Weber imprecision model, unlike reinforcement learning and the softmax noiseless equivalent, can perform virtually as well as the theoretical adaptive optimum in each of these environments. However, in this simulation, three parameters lambda and mu that scale the noise have been adjusted to each environment, which contradict, of course, the assumption that there are noise parameters, that is, these noise parameters cannot or should not be adjustable. So to circumvent this issue, we use a different approach, which is what we call the minimax approach. So what is the minimax approach? For every pair of three parameters, lambda and mu, we consider the loss of performance relative to the theoretical optimum in every environment and compute the maximal loss, max loss, over all the environment. And then we choose the parameter lambda and mu that minimize this maximal loss. So this refers to minimax loss. So this minimax loss actually is a measure of the model versatility across the uncertainty about the temporal structure of the environment. And it measures the model versatility or the model robustness to the variety of environment or the unknown about the temporal structure. For the Weber imprecision model, the minimax loss is 9% compared to the theoretical adaptive, the theoretical optimal. And as you see here, it's obtained for a large value of lambda, which scales the Weber noise, and a quite small value of constant noise. So we can use the same approach, the minimax approach, with the other model, adjusting the parameter to compute this minimax loss. And what we observe here is that the model with the lowest minimax loss, that is the most versatile model, is actually the exact constant volatility model. But the second one is the Weber imprecision model. Whereas all other models I presented to you the forward approximation of this exact constant volatility model perform less. All reinforcement learning model, Pearsall reinforcement learning and so on, perform similarly to this forward constant volatility model, whereas more sophisticated model, even their forward approximation, actually are perform very poorly. That is, are very poorly robust to the uncertainty about the environment, the temporal structure on the environment. So the second result is this one. The most versatile model with the lowest minimax loss is the exact constant volatility model. With no knowledge about the environment structure, this appears the optimal model. However, this model is biologically implausible because I just show you that its forward approximation perform quite poorly, is much less versatile. Interestingly, the second best versatile model is the Weber imprecision model. With no knowledge about the environment structure, it appears the most optimal model among biologically plausible models. So the question now is whether this, so it's a rather interesting model, and it's if you remove backward inference, it appears to be actually the most robust model to the ambiguity about the temporal structure of the environment. So we ask the question whether actually this model can best explain human performance in this kind of volatile environment. So we use this kind of protocol we use for simulation, the task with reversal, with a variable volatility, and one arm rewarded with 80% probability, the other one rewarded with 20% probability, and you have reversal with variable volatility. So we use several levels of volatility here, according to the episodes, and here this is the reversal that occurs according to this volatility. So what we found that if we compute model posterior probability, that is the exact model likelihood marginalized over parameter space. For this, we use also particle filtering because you cannot compute it exactly. But with particle filtering was a very good approximation of this model posterior probability. We see that actually the Weber imprecision model fits the best human subject, and even with a very significant XE. And we can assess the validity of this procedure with the model recovery procedure. And you can see on the diagonal, each model actually fits its own performance better than the other concurrent model. So in this kind of closed environment, compared to other Bayesian inference models, the Weber imprecision model, which is less complex, very basic model, actually fits the best human performance. But it fits also much better than reinforcement learning, all reinforcement learning model. Here this is model comparison between each of the Bayesian inference model and the best fitting reinforcement learning model to human data. And you see that across this model, only the Weber imprecision model fit better than reinforcement learning. And you can see also that consistently that on the reversal curve after a reversal, so the adaptive curve from subject, that for every model you have some discrepancy between model performance, the best fitting model, and human performance. Whereas for the Weber imprecision model, you see that there is no significant discrepancies. So this is consistent with the quantitative model fit. Interestingly, the Weber imprecision model fits better than its reduced model. So it fits better if you better than the model when you remove the Weber component, with an exceedance probability very close to 1. And also the Weber imprecision model is better than its determinist equivalent, where you assume determinist imprecision. So you remove the stochastic part of noise, and you assume simply that the entropy of posterior belief vary as the Bayesian surprise, with no noise in the procedure. And again, we have a very high exceedance probability in favor of the Weber imprecision model. So in open-ended environment, we use this protocol, the same as in simulation actually. So we presented subject digits, 3 possible digits. There are 4 possible actions. They select one of the action and they got a positive reward. So for the correct response, they got the positive reward with 90% probability. And for the incorrect response, they get the negative feedback with 90% probability. So there are 10% of noise. And of course, there are there is a constant volatility. So this reward contingency switch with this probability. So here in this protocol, we found that all Bayesian inference model fits human performance better than the reinforcement learning model. And this is because there are some reoccurrence of external contingency across hidden state. And of course, the reinforcement learning model cannot capture this reoccurrence. Whereas human subjects did. However, again, the Weber imprecision model perform better and fit better human performance than this other more complex volatility inference model. Whereas this is the exact model of the forward approximations. Again, I mean, the model recovery shows that the Weber noise model fits its own performance better than the other model, and this is true for every model. So the protocol and the fitting procedure is valid in disentangling the different models. So just to conclude this short talk, Weber imprecision model accounts for human performance in volatile environment better than Bayesian models inferring volatility, also better than their biologically plausible approximation and reinforcement learning model. Interestingly, and from an evolutionary perspective, precision in first order inference. What's that? Can you hear me?
We had some problems before, but now actually you don't share the screen any longer. At least I can't see.
I switch it off, but can you hear me now? It's okay?
Yeah, it was just the last part of your presentation before the conclusion that was a little bit distorted.
Okay, so let's go again.
It was basically when you had the matrix. Yeah, this part was highly distorted.
So this slide was just to show you that also in the open-ended environment, the fitting procedure and the protocol can disentangle the different models. So the Weber noise model fits better its own performance than the other model, and it's true for every model. And so to conclude this talk, Weber imprecision model accounts for human performance in volatile environment better than Bayesian models inferring volatility, and also better than their biologically plausible approximation and reinforcement learning models. Weber computational imprecision in first-order inferential process dismiss the complexity of inferring volatility. So this is, in my point of view, a critical advantage, evolutionary advantage. And this may explain the lack of evolution pressure to reduce computational imprecision in brain inferential processes. And of course, this implies that in canonical decision tasks, this results in suboptimal behaviors. But in changing and variable environment, this Weber imprecision this Weber imprecision allow actually to adapt very close to optimality without the complexity of inferring volatility. And thank you for your attention.
Thank you very much, Etienne. We have time for questions right now. I think it was very well in time. We're actually ahead of time. Maybe I'm reading the first question. Give me a second. So the first question is by Vasiliki Liakoni, and she asked, did you test an alternative RL model with some change point detection mechanism or Weber noise perturbation? Maybe I read it again. Did you test an alternative reinforcement learning model with some change point detection mechanism or with some Weber noise perturbation?
Yes, I mean, I'm not sure I understand the question. All the models I presented are change point detection model and based on Bayesian inference. So there are, of course, other models that was proposed in the literature, but they are very complex, and the model we propose is actually one of the simplest models you can imagine to adapt to this changing environment. The key point is that in this model you have no change detection process. This model shows you, the Weber imprecision model shows you that you don't need to detect change. You just need to have some noise that add to first order belief about external contingency to be flexible enough to rapidly change the belief about the environment.
Great, thank you for the question. The next question from the audience is from Sandrine. She asked, if we assume that noise is key to human information processing, then where does this noise come from? What are the factors that induce noise in the brain? And this might be a silly question, but I'll insert no questions are silly. Do quantum effects play a role here?
What is the silly part of the question?
Do quantum effects play a role in noise in the brain?
Okay. So where does the noise come from? The noise comes from the, I mean, anyway, any physical device, of course, compute information with some imprecision. The question is whether it's valuable to decrease this imprecision, so to have more neurons, for example, and so on, or not. And what we show here is that actually it's maybe valuable to have enough noise and to keep some noise in the process, and especially if they follow the Weber law. Following the Weber law is a very natural law, actually. It means that simply the more you change your internal representation, the more they become noisy. And as I show you, I think it's a very valuable strategy for to be adaptive in changing environment. And so about the silly part of the question, about the quantum question, I think there is nothing to do with any quantum theory here. I mean, noise is simply imprecision here. It could come from synaptic noise, from conductance noise, or whatever. But it's valuable to have enough noise, provided that they follow the Weber law.
Great, thank you so much for the answer.
Okay. Then we have the next question by Arthur Barak. And he asked, does the Weber imprecision model follows human behavioral data when the noise level is increased?
No, of course. I mean, if you increase too much the noise, then the performance decreases a lot, actually. So there is, maybe I can show you the slides. So there is a range over which it's not so important. Maybe I can share my screen again. Okay, here you see that you can achieve optimal performance over a range of lambda parameter, which is quite large, actually, from 1 to 2. And of course, the constant parameter here should be close to 0, but it could vary a little bit. So, of course, if you increase the Weber noise, then the performance becomes very, very low, and much lower than human performance too. So there is an adequate level of noise which leads to optimality. And in terms of fitting human behavior, it's similar. If you increase the noise, then you depart from human behavior at some point.
And in some way, you would say that's then why basically, it's this way you could basically determine the noise level. Is that what you're saying?
Of course, yes. So the important thing is that the exact value is not so important because it's noise, of course. So there are a lot of stochasticity.
Great, and I think we have time for another question. Is that right, Michael?
Oh, we have time for a lot of questions.
Oh, great. Okay, perfect. Sorry. I got the schedule a little wrong. All right. So the next question is from Alessandro Marin Vargas, and he asks, how would you justify the positive effects that Weber imprecision in the internal state has on performance? I.e., is it only a source of variability?
No, of course. The advantage is that in the zero volatility model, so it can infer, this is the model that infer the fastest the current external contingency, because it has not the burden to infer some volatility. So this is the one that converges the fastest to the current external contingency. But of course, it means that if this external contingency change, you need a lot of time to switch from its posterior belief to the new external contingency. So the Weber noise allow actually, because you add some entropy to posterior belief when there are a lot of change in your posterior belief, so it allows to quit this posterior belief and to rapidly switch to the new contingency. And exactly this is what do the volatility. in the more sophisticated model. Inferring increased volatility means that you you increase the entropy of your posterior belief. So this is the intuition. The more you infer higher volatility, the more you increase the entropy of your posterior belief. And this is exactly what do the Weber noise.
Great, thanks so much.
And our next question is by an anonymous attendant. And the question is, if the best model is the one with exact constant volatility, and if the only problem is its biological plausibility, then why didn't you try other approximate algorithms? And second question related, instead of adding computational noise to a simpler model.
And I'm sure I get the point of the question. Can you repeat it?
Sure. It's a long question. If the best model is the one with a constant volatility, and if the only problem is its biological plausibility, then why you didn't try other approximate algorithms instead of adding computational noise to a simpler model?
Okay, so what we tested in this study, the most important approximation of this exact constant volatility model, which removes the backward inference processes, which are biologically implausible. So we have the best approximation of this model, which is a forward approximation. That it is exactly the same model, but you just remove the backward passes in the inferential process, or in the implementation of the inferential process. And as I show you, actually this forward approximation of the exact Bayesian, exact constant volatility model is very poor, actually, is poorly versatile, and it doesn't fit very well human data too, at least less than the Weber and precision model.
Great. So we have another question from Pablo. To the question about why has evolution favored computational imprecision, could it be related to the optimization of energy consumption? Trying to reasonably approximate sampling while keeping energy consumption relatively low?
Yes, of course. This is, you get something advantageous, the ability to adapt flexibly to changing environment for free, and even by decreasing your energy consumption, because adding more noise means that you consume less energy to be precise. So it's a double advantage.
Yeah, that's great. We have a bit more time actually, so maybe some of the panelists here could chip in with questions. I don't know if other speakers want to question our current speaker. Oh, there's one more question. Sorry, maybe I'll let Michael give that one then.
The next question is by Hasam Tutonji, and the question is, why is imprecision considered marks of suboptimal behavior and not to behavior optimized for environment statistics, for example, prior experience of volatility?
Why is imprecision considered marks of suboptimal behavior and not to behavior optimized for environment statistics? What does it mean? I'm not sure I understand the question, actually. Even when reading it, it doesn't make sense for me, the question. So maybe if you can reformulate the question, maybe the person who asked the question.
Yeah, maybe Hazem, you can reformulate it.
Yeah, maybe I can guess in the meantime. Maybe the question is about whether or not like imperfections in behavior are actually related to suboptimality. Like, is it really getting back to maybe thinking about explore versus exploit, right? Like noise isn't always bad. So maybe is the framing of the question Yeah, let's see. Is the framing of the question about like, is it really about being suboptimal, or is it about somehow being optimized to the environment and maybe noise is useful? If I could guess from Hazem before he chips in.
The one issue is that it's very difficult to talk about optimality in a general sense. Optimality is always referred to a specific protocol. It doesn't exist a model which is in general optimal. It's a wrong notion. So here, what the advantage of noise is that it's very robust, or at least Weber noise. It's very robust to the absence of knowledge you may have about how your environment is structured. So I think the notion of robustness is maybe even more important than the notion of optimality, because in general you cannot be optimal. This notion it cannot be very well defined in general. It can be defined only within a given protocol or a given environment.
It seems to be Hazem was quite happy how Mackenzie summarized it.
Okay, great. Excellent. Thanks, everyone.
So maybe we have one last question, maybe two more. So here we got a question from an anonymous attendee, and he or she asked, can we measure if neural noise actually follows a Weber law?
So as you know, the Weber law is a psychophysics law. But there are some models, neuronal models, that link this psychophysics law to Gaussian noise in neural processing. So that's a first answer. The other answer is that we are now preparing a paper with fMRI where we access neuronal activity, at least coarse measure of neuronal activity, and we were able actually to capture. We show that actually the Weber law noise capture exactly the activations that were identified as co-varying with the volatility.
Okay. Thank you very much, Etienne.
Thank you very much for your attention.
Interesting and challenging talk.